Welcome to your Daily Dopamine
with Dr. Joe McCullough,
where we deliver daily doses of education, entertainment, and inspiration. So sit back, relax, and get ready to be
Dopamine, dopamine, dopamine.
Oh
yeah. Just thought I'd have a little fun musical introduction to start off with. So I'm here in the classroom and it's a packed house, me and nobody else. And so I'm not quite sure how these video online lectures are going to go. I'm going to try and do a little recap right now on the board and a example problem. And then what I think I'm going to do is go home and try doing the same thing or a different example problem on my computer using Camtasia and a webcam and a little writing tablet, and we'll see how it goes. So this is first attempt. Stay with me. I will send out email updates on a regular basis. But right now my plan is to collect the homework, collect the PLCs, collect the labs once we get back to having live lectures and stuff online or on campus. And in terms of quizzes, I'm thinking about just not doing quizzes until we get back. Although now it's, let's say, April 10th, so we'd miss basically this week and 2 weeks of classes after spring break. But yeah, right now my intention is not to have any online quizzes or anything like that, but that could change. So let's do a little recap and yeah. Okay, so let's start with a little recap. So far in Chapter 8, I've only spent Thursday on it. But keep in mind, Chapter 8 is the fourth of 4 chapters on Newton's laws, and there's not really a whole lot new. Basically, it's Newton's laws using circular motion. So dynamics 2, motion in a plane, really we're just doing Newton's laws where something is moving in a circular path of radius r at speed v. So one, just to be clear, if the speed is constant, and if we know the radius and the period, we know the speed is given by v equals 2 pi r divided by t. That's for uniform circular motion if we know the speed of the object is constant. But either way, if an object is moving in a circular path of radius r at speed v, it is accelerating because the direction is changing. The radial acceleration, we've seen this before, but the magnitude of it is v squared over r, or v is the speed in meters per second, r is the radius of the circular path in meters. That gives us the magnitude, the meters per second squared. The direction is always towards the center of the circular path. So if you remember, Newton's law, sum of the forces equals ma, this is really a vector equation, which means we can break it up into x and y components. So we've got the sum of the forces in the x direction equals max, sum of the forces in the y direction equals may, and then if we also had the z direction, sum of the forces in the z direction equals maz. Here's the thing. In this chapter, Chapter 8, the object is going to be moving in a curved path. Not necessarily a complete 360-degree circle, but a car going over a hill, a pendulum swinging back and forth, and if that's the case, then one of the components of the acceleration, either the x component or the y component, is going to be radial acceleration v squared divided by r. So that's a quick little recap, and let's do a really basic problem as an example, and then I'm going to try a more complicated problem at home using a little writing tablet, and we'll see how that works out. Okay. Off with the recap, on with the celebration hats slash let's do example problems in front of an empty classroom and try and maintain my positive energy hat. Woo! So, example problem is basically dealing with an object like a ball being swung in a vertical circle and looking at the tension at the highest and lowest points. So, this particular problem, a 1 kilogram ball is swung in a vertical circle of radius 0.4 meters at a constant speed of 2 meters per second. What is the tension at the highest and lowest points? So one, let me throw this out there. It's not really possible to swing something in a vertical circle at a constant speed. We'll get to this once we get to conservation of energy, but it's going to be changing its speed as it's swinging. So I just want to throw this out there. This is not a realistic problem. The speed would be changing as you are swinging this thing. However, let's assume it has a constant speed of 2 meters per second the whole time. So the big question before you start is, what's different about the very highest point as compared to the very lowest point? And the answer is two things. One, radial acceleration always points towards the center of the circular path, which means at the very highest point, the radial acceleration is pointing down towards the center, but at the very lowest point, the radial acceleration is pointing up towards the center. And then if we were analyzing it, to the right or to the left, it's always pointing directly towards the center of the circular path. The other thing that's different is tension. At the very highest point, tension's going to point straight down. At the very lowest point, tension's going to point straight up. So how you do this is the same way you do any single Newton's laws problem. Identify the known and, I'm sorry, that's not Newton's laws. Basically identify the forces acting on an object, draw a free body diagram, break the forces up into x and y components, apply sum of the forces equals ma to solve for your unknown quantity. The only difference is really the acceleration v squared over r towards the center of the circular path. So, setting it up, let's look at the highest point. So at the highest point, if I draw my free body diagram, remember we only really have two forces. I've got tension and I've got gravity. At the highest point, tension is acting straight down. Gravity mg acts straight down. And in this case, the acceleration in the y direction is our centripetal acceleration v squared over r. So what I'm going to do and what I recommend that you do, and I've said this before, define positive in the direction of the acceleration so you don't forget to use a negative a if the acceleration's in the opposite direction of positive. So just to be clear, I'm defining my positive y as down. Don't really need x, but to be complete, positive x to the right. So if I do the sum of the forces in the y direction equals may. Remember, sum of the forces is always forces in the positive direction minus forces in the negative direction. In this case, I've defined down as positive. Both of my forces, tension and mg, are in the positive direction. So the sum of the forces in the y direction just becomes tension plus mg. And again, acceleration points down, but I've defined down as positive. So I get my acceleration is just v squared over r. So what we get at the very highest point, tension plus mg equals mv squared over r. Solve for tension and you get m times v squared over r minus g. So putting in our numbers, we get tension equals, what do we use? 1 kilogram times 2 meters per second squared divided by 0.4 meters minus 9.8 meters per second squared. And something doesn't look right there. And in this case, I believe for, divided by 9.8. So I thought that the tension was not going to come out to be a positive number because I just made up these numbers, and it does work out. So actually, I've got 2 squared divided by 0.4 minus 9.8 times 1. So what I get is the tension at the very highest point is 0.2 newtons. And so just, if I make any little minor mistakes, I'm not going to try and edit everything out. So what I was concerned at is that this v squared over r was going to be less than 9.8, in which case my tension would have come out to be negative, which can't have a negative magnitude. So a little question for you. What would it have meant if I had solved for the tension and it came out to be negative? The answer is I had an unrealistic problem. What it would have meant was that 2 meters per second wasn't fast enough for this thing to do a complete loop-de-loop, and it would have fallen at the top. But luckily 2 meters per second is very close to the critical speed, and in fact we'll do that at the very end. So let's save this tension equals mv squared over r minus mg. We're going to come back to that. So this is at the highest point. So our tension at the highest point, 0.2 newtons, still above zero, which means the string is still taut, so it can make a complete loop-de-loop. So now let's do the exact same analysis, looking at the sum of the forces on the very bottom. So now instead of the highest point, we're looking at the lowest point. Two differences. One, when I draw my free body diagram, keep in mind tension is acting straight up at the lowest point. Gravity still always acts straight down. And in this case, acceleration is towards the center, which at the lowest point is straight up. So acceleration in the y direction is v squared over r. So to be clear, I'm going to define up as positive in the y direction. So now when I do, the sum of the forces in the y direction equals may. What I get is tension minus mg equals mv squared over r. So tension equals m times g plus v squared over r. So what I get is 1 kilogram times 9.8 meters per second squared plus 2 meters per second, the quantity squared, divided by 0.4 meters. Plugging everything into our handy calculator, 4 divided by 0.4, 10 plus 9.8 times 1. What we get is tension is 19.8 newtons. So, tension much bigger at the lowest point, tension smallest at the highest point. So now let's modify this problem and see what is the minimum speed you need at the highest point so that the tension, the rope remains taut. Basically, the tension is greater than zero, which means this string is still taut as this thing goes over the highest point, meaning it can do sort of a complete loop. If the tension went to zero, that means at the highest point, this mass, this rock, whatever it is, this ball would drop. So, let's go back to the highest point, what we found at the highest point. Was that tension was mv squared over r minus mg. And if I want the string to remain taut, the tension has to be greater than zero. So I want my tension to be greater than zero, which means I want mv squared over r to be greater than mg, which means I want v squared over r to be greater than g. We've seen this come up before. Basically, if this ball is going to move in a complete circle at the highest point, I have to have the radial acceleration, which in essence is the acceleration because of a change of direction, be greater than my acceleration due to gravity, which in a sense I could think of this as a change in speed. And I can think of my radial acceleration as a change in direction. So basically at the highest point, I want the acceleration of this thing moving in a circular path to be greater than the acceleration of it dropping straight down and increasing its velocity by 9.8 meters per second every second. in the y direction. So we want v squared over r to be greater than g, which means we want v squared to be greater than rg. So we want v to basically be greater than the square root of rg. You'll see this quantity comes up a lot. We call this the critical speed. It's also the speed at which, well, I've already touched on this, but if something were to do a loop-de-loop, like in a roller coaster where this cart was not connected to the track in any way, so it was just sort of going around the outside of the track, that would be the speed you would need at the highest point to not fall off. And I did another example problem where if you were on a car going over a hill, the critical speed in this case is the maximum speed you can take a hill at of radius r and still maintain contact. All right, so that's a little example problem. I'm going to go home and try and do another example problem using a writing tablet and a webcam. Put them all together, post it to YouTube, and then we'll see how it goes. Just so you know, we are all figuring this out. It's sort of unprecedented in your lifetime, and it's unprecedented in my lifetime. So please be patient, and yeah, I'll figure this out. What's the best way to present information? So stay tuned. You'll get this video sometime today. Okay, here we go with the first test of using my webcam and a Wacom tablet to do some example problems. So first I want to do example problem 8.13 and then another example problem that's not in your example packet. So a little reminder, chapter 8, all about Newton's laws except circular motion. So everything we've done before still applies. The only real difference, one of the components of the acceleration, either ax or ay, is going to be v squared over r towards the center of the circular path. So let's take a look first at problem 8.13. So what we have is mass m1 on the frictionless table of the figure below is connected by a string through a hole in the table to a hanging mass m2. With what speed must m1 rotate in a circle of radius r if m2 is to remain hanging at rest? So here's a case, m1 is moving in a circular path, so we know it's accelerating and the acceleration is v squared over r. m1 is hanging at rest, it's not moving, so the acceleration is 0. Just like before, we look at each object, apply Newton's second law, sum of the forces equals ma, solve for our unknown variables. So let's first take a look at mass 2. Oh, I thought I deleted that button. All right, should be disabled. So mass 2. Only two forces acting on mass 2. I've got tension acting straight up, and I've got weight, gravity, m2g, acting straight down. I'm going to define my axes so that x-axis is positive to the right, y-axis is positive straight up, and this object is not accelerating. So we know the sum of the forces in the y direction equals may, which in this case is 0 because the object is not accelerating. Sum of the forces in the y direction, forces in the positive y direction, minus forces in the negative y direction. So we get, in this case, tension minus m2g equals 0. So one equation, I've got tension equals m2g. Here's one equation. I don't have m2, so I don't know what the tension is. But we have another mass we can look at. Let's look at mass 1. And let's assume mass 1 is basically someplace so that it's more like over here. So if I look at the forces on M1, I've got tension acting to the left. I've got the normal force acting straight up, and I've got gravity M1g acting straight down. So this is sort of a view of M1 from the side. The normal force is acting straight up from the surface. Gravity is acting straight down. And tension is the force from the rope, which is actually causing it to continue moving in a circular path. So I could look at, so one, let me just define my axes. I'm going to define my x-axis as positive to the left. Y-axis is positive straight up. And the reason I'm defining it to the positive to the left, because it's actually accelerating to the left, and the acceleration is v squared over r. And again, I'm assuming the mass is sort of in the figure, kind of like the mass is right here. So the mass is sort of at a 90-degree angle. So I could look at the sum of the forces in the y direction equals MAY, which in this case is 0 because there is no motion in the y direction. If I wanted to, what I could get is that the normal force equals M1G. Don't really need that in this case. Second one, I've got sum of the forces in the x direction equals MAX. In this case, the only force in the x direction is tension to the left. I've defined to the left as positive, so what we get is tension equals M1 times AX. AX is V squared over R, so what we get is tension equals M1 times V squared over R. So here is a second equation. So I've got one equation that says, let me try and change colors here. So we got one equation that says tension equals M2G, and we got that from the fact that M2 is at rest. Second one, we've got tension, and even though we don't have a massless, frictionless pulley, the tension's still going to be the same everywhere in a rope. So I've got two equations. Let's set them equal. So both equations are for tension. So I'm going to set tension equals M2G equal to tension equals M1V squared over R. And what I get is M2G equals M1 times bear with me here. M1 times V squared over R. Solving for V, we get V squared equals M2G times R over M1. Our final answer is our speed is the square root of M2G R over M1. So again, nothing really new. We've just got Newton's laws being applied to two different masses. So mass 2 was the hanging mass. The only forces were tension acting straight up, gravity, M2G acting straight down. Mass 2 wasn't accelerating at all, so the sum of the forces was 0. We got tension minus M2G equals 0. Tension equals M2G. Second mass is moving in a circular path. And in this case, I'm assuming that the mass is just to the right, and we're looking at it sort of from the side. Tension is acting to the left. We've got the normal force straight up. We've got gravity straight down, and the acceleration is towards the center of the circular path. We get sum of the forces in the x direction equals MAX. Tension equals M1 times AX, where A is V squared over R. So tension equals M1 V squared over R. Set these two equal, we get that the speed V is given by the square root of M2GR over M1. All right, deep breath. All right, let's try the second one. So this example problem is not in your packet. So you've got a swing ride at a carnival consists of chairs that are swung in a circle by a 15-meter cable attached to a vertical rotating pole as shown in the figure. Suppose the total mass of the chair and its occupant is 195 kilograms. What is the tension in the table attached to the chair? What is the speed of the chair? So here, keep in mind again, we've got somebody moving in a complete circular path. I know that the sum of the forces acting towards the center of the circular path has to be ma, and a is v squared over r. So again, I've only got, in this case, if I look, two forces acting on the chair and the person combined. I only really have tension and I've got gravity. So if I draw a free body diagram, I've got tension and I've got gravity, mg. And the angle they gave us of 60 degrees is this angle right here, which from alternate interior angles or whatever that is, this right here is 60 degrees. So let me just break this right up into x and y components. And to be specific, I'm going to define my y component as positive straight up, my x component as positive to the left, because that's the direction of the acceleration. And, whoops, the acceleration is v squared over r to the left. So I'm going to break this up. Here is my hypotenuse. This is my adjacent side, so it's going to be t cosine. So I've got t cosine of theta. I don't like the way that looks. I've got, silence my phone. I've got t times cosine of theta, where theta is 60 degrees. I've got mg, and I've got t sine theta. So this thing is not moving up and down, we're assuming, which means there is no motion in the y direction. So the sum of the forces in the y direction is 0. So if I apply Newton's second law, sum of the forces in the y direction equals may, which is 0. I get t times the cosine of theta minus mg equals 0, or my tension equals mg divided by cosine theta. So my mass, 195 kilograms, g, 9.8 meters per second squared, never, never, never negative 9.8, divided by the cosine of 60 degrees. And what you'll get, if my math is all right, is 3,822 newtons. This is what the tension is, and we got that from the fact that there is no acceleration in the y direction, so sum of the forces in the y direction has to be 0. Okay, so that doesn't give us b. What is the speed of the chair? Now we need to look at the sum of the forces in the x direction equals max, which is mv squared divided by r. So we've defined to the left as positive because that's the direction of the acceleration. The only force acting to the left is t sine theta. So what I get is t sine theta equals mv squared over r. Let me just skip a step of algebra, and what we're going to get is v is the square root of mt. Whoops, that's not right. V is going to be the square root of third time's a charm. V is going to be a square root of RT sine theta divided by M. Now, the only tricky thing here, the radius is not 15 meters. It's the radius of the circular path in which we're going. So let me just sort of do that over here on the right. If I look, what I have is, here's my hypotenuse, which is 15 meters. Here's my angle theta, which is 60 degrees. And r, the radius of the circular path, is actually right here. This is my opposite side to this angle. So what I get is r is 15 meters. times the sine of the angle, which is 30 or 60 degrees. So what I get is the radius is actually 13 meters. So when I go back and put all of my values in here, what I get is V is the square root of 13 meters. The tension we found was 3822 newtons times the sine of 60 degrees. All this divided by the mass, which was 195 kilograms. What you're going to get for the speed is 14.9 meters per second. So there you have it. I'm not sure how I'm going to continue doing lectures. It's a little hard using this tablet, but I don't know if coming into the classroom and lecturing to a blank classroom is the way to do it either. So anyway, I'm working this out and hopefully be figuring this out, and I'll keep you updated. But this is your first online lecture for 4A. Whoop, whoop. That's it.